Alright, I'm doing it, guys. Hello, hello, hello. Good morning. Got the sounds of mowing in the background today, and birds very, very loud. Hope everyone's doing well. I have some video examples to record, so I'll be doing that a bit this afternoon. We're on chapter 11 in the physical book, section 3, and we're working on polynomials. We're probably going to talk about section 3 and 4, maybe a little bit of 5. They go hand in hand today, and then we'll take it from there. Let's hope you all can hear me, since I don't have a picture up yet. All right. So I think Janine asked if the screen was blank. Yes, it was. I didn't have any good drawings up this morning. All right. And everyone dropped away. Let's see, that was probably me having the screen blank on you guys there. Give a second here, see what happens. All right. Okay, so we're going to look at polynomials, and we're going to define them. They are probably one of the more important parts of what ends up being the algebra. And they're made up of an algebraic expression. And they have a base part. So they're an algebraic expression composed of one or more monomials added, and of course we say so added or subtracted, since those are the same thing. Or at least we should be appreciating that they can be viewed as the same thing, added or subtracted. And of course, this definition goes, well, hey, pray tell, what's a monomial? So monomial is a collection of constants and variables multiplied together. And so I have always found mathematical definitions to be a bit odd, so I like showing examples more than anything else. And our focus will be on the polynomial. We're going to have to look at its building block, the monomial. And so what we mean by that is constant 3, that's a monomial. Sorry, oops, I lost my 3. There we go. X, that's a monomial, right? Just this 3x squared is a monomial. Notice they're connected by series of multiplications. Additions and subtractions do not connect them together. Negative 3x y to the fifth z. This is a monomial. It's a collection of a whole bunch of variables put together. Things you won't see in a monomial: the powers are positive. So that's you should see. Right? Positive powers only. And integers. So let me put in no. You will not see square roots or cube roots in a monomial. You will not see 1 over a variable. Yet, we'll find a way to deal with them. Polynomials, this number is always a positive integer. And they consist of variable terms. Now, one of the things, and the reason additions are very special with these, and why we were looking at place values and numbers for the additions, I'll scroll up here, is if I have 3x and I add to it 5x, we can think of, I have 3 of these, and they're the same thing. I have 5 of these. Altogether, I have 8 of them. And we call this collecting like terms. But if I have 4x cubed and I add to it a lowly x, these terms aren't like. This is a series of multiplications. And because I don't know what these multiplications are doing, I don't know what the effect of adding one more x does. So this is as simple as this gets, 4x cubed plus x. And that becomes our game with polynomials and monomials. Is this thing here is called a polynomial. It has multiple monomials in it. Poly means multiple. And so these multiple monomials come together. If the terms are the same, like up here, we simplify them. And we gather all of the things with the same names together. So I'm going to look at some examples of monomials and polynomials and what we can do with them. So I think I'm just going to look at some of the exercises in the book and put them together. All right. So if I have 7x squared plus 2x squared these have the same name. So I can look at it as saying I have 7x squareds and I have 2x squareds. So altogether I have 9x squared. I collect my like terms. I count up how many x squareds I have. Again, this is called collecting like terms, and it's what we do with monomials that are added or subtracted together to simplify our polynomials. All right. So if I have a collection of monomials put together, there are two things we can do. We can talk about the number of variables. So in this case, there was one variable. It was x. And so that would be a polynomial in one variable, x. I can also have different variables represent different things. So a very common variable that we see is t for time. And I could have 1/2. Let me put a 9 up here. I'll put 9.8 because I'm going to be weird. T squared plus 32t plus 4. This is a polynomial in one variable t. Right. And you'll find as you do mathematics, the name of the variable doesn't matter as long as it distinguishes it from other variables. Good morning, Stacy. And we can have a polynomial in more than one variable. So I could have x cubed y plus 3 x squared y squared plus 4 x y cubed, and this is a polynomial in two variables, x and y. Most of what we do is we're going to focus on polynomials in one variable. In fact, this book introduces two variables just so you know they exist, but almost everything, there might be one or two questions where I ask you to identify one or two more than one variable polynomials. But for the work we're doing here, we're going to do the one variable polynomial, and mostly in x. And so the other way we are classifying a polynomial is what we call the degree of the polynomial. And the degree is the largest power of the variable. So I have 4x to the 5th minus 2x. The largest power is 5. This is a degree 5 polynomial. If I have 8x cubed plus 9x squared minus 7x minus 1. There's the largest power. That's a degree 3 polynomial. Now notice I'm showing them and I'm repeating the concept. I have found that the definition in words doesn't make much sense until you start doing them. So I'm going to keep putting up the examples of polynomials. I'm going to call them polynomials. And we're not solving anything yet. We're saying this is what this thing is, right? And I know the tendency is, what is x, right? Well, we're going to find ways to manipulate these things. But we kind of have to look at the form that they have so we can figure out what's going on. Because underneath it all, we're going to be able to put values of x in here. In fact, you've already looked at one type of polynomial. You've looked at a degree 1 polynomial that we called linear. And you could think, hey, let's see, 1, 2, 3, 1, 1, 2, 3, 1. All right. Close enough. So I get my straight lines there. That this polynomial in 1 degree made a line. And that actually has meaning. And that's kind of where we're going with this, is the different degrees have different behaviors. And so you've looked at degree 1 polynomials and they were lines. We did a lot of time figuring out what lines did. And lines don't go away. Well, degree 2 polynomials, I'm going to hint at something that'll become a little more important in a day or two. Degree 2 polynomials, the simplest one is x squared. That doesn't form a line. It forms this shape called a parabola. And we're going to learn that there's different shapes and behaviors for different degrees of polynomials. And we're going to use that to help us. But what we need to do is build them and take them apart and look at them. Because this is the simplest degree 2 polynomial, it can look more complex than this. And so we need to kind of name the parts and figure out what to do with the different parts. We need to do different algebras with it. So one thing we do when we write our polynomials is we write them in descending order of power. Now remember, I just showed you that line up there. I did the 3x plus 1, and we wrote those. I'll put a y out front so that we can graph it. We wrote this in a form so that our slope was hanging out front and our intercept was hanging out front. This form had value for us. There was another way of writing linear things, which was the ax plus b, and we'll look at that in a little more detail. But for polynomials, we write the highest power first, and whatever its coefficient is. So we'll say 4. I'm going to give an example here. 4x to the 5th minus 3x to the 4th plus 8x cubed plus 2x squared minus x plus 1. So the highest power goes first, and I go down in powers. All right, and we know that's to the 1, and a constant, we could think about x to the 0, because anything to the 0 power is 1. And this lets us focus on particular things. It lets us see the degree right off the bat, and this constant is important. And so by putting in a descending order, by always having the power in the descending orders, we have a form so that we can work with our polynomial. So this is the space we're in. I'm going to throw a couple names at you of some specific types of polynomials, and then we're going to start adding and subtracting and doing some algebra with them. These names are not important in the fact that, well, classifying things by name has some importance, and there's some important patterns. And so the number of pieces in here makes up some special polynomials. And so we already said they were built of monomials. So if I have one term, it's a monomial. Right? Mono, one. So one named part. If I have two terms, 3x minus 2, this is a binomial, like a bicycle, 2 parts. And if I have 3 parts, it's a trinomial. And we basically stopped naming after these 3 and call anything with more parts a polynomial. They are all polynomials. But for us. And the reason we're going to be looking at these is, notice, I can build a binomial out of two monomials. I can build a trinomial out of the addition of three monomials. And any polynomial, the definition of a polynomial, is built from many of these little parts coming through. And so that's the first thing, is this is used to build everything else. Builds with addition. Right? The monomial builds with addition. And that's our focus today, is addition and subtraction. So we're going to be using monomials to make larger polynomials. And then in our friend the trinomial is built from binomials built with multiplication. Builds with multiplication. So I can multiply binomials together to make trinomials. I can also, and then in polynomials are a combination of putting these together. And so that's why we try to name them different things so we can see them. Now, I know I'm talking in an abstract here, right? I'm talking about these mathematical things and we haven't done anything with them yet, but identify them. And what we're doing by identifying these different patterns is trying to get a way of classifying things. So I'll say we have already done something with polynomials. We have that linear form, right? This is a first degree polynomial which is a line. And we saw the utility of the line. We could see this as being a rate of change. And this is a starting point. And so we could build linear equations where they had rate of changes. So the utility of these is second degree polynomials. And I'm just putting, right, these a's are any number, but our variable is x. Well, these form parabolas, which look like this. And they have a very well-defined minimum, or if it's flipped up, maximum value. And so what ends up happening is about 95% of the problems that we model in mathematics, you can make into a line or a parabola, right? You can focus on I can have data. I'm going to show you what data sometimes looks like here. So I have data. And my data, if I were to plot it in a graph, ends up looking crazy, right? It's all over the place, does some odd things, right? And I need an equation because let's say this is what my money is doing. And I want to know when I get here, because I'm putting money in to maximize my return, but I want to get as close to this point as possible because if I stay too long, I'm going to dip down and I'm going to lose my money. I don't know why I always talk money investments. I'm not a money-centric person. I sometimes think the rest of the human race is. So I go, well, the importance of this stuff is we know what to do with our money. But this could be physical fitness. It could be, there are models we can have when we can look at the data, and there's points of maximization. Well, I could figure out the polynomial that defines every bit here. But if I'm only worried about things within this space, I can model this as a parabola, a second degree polynomial, and I can find places of value. And so the reason we study these bits and pieces are most problems that we can face, we can solve as a second degree polynomial or a line. And if we can get by doing most things that way, it's worth knowing the language that makes these things. And just like the addition and subtraction that we went through, we have to kind of learn the place of the symbols. And so that's why we're going to focus on monomials, binomials, and trinomials. Of course, we're going to learn all of its language to put it together. So the first thing we can do with these things is we can add them. And adding and subtracting is done by, addition and subtraction. Yeah, I'm not having a blackboard. I think my hand is going on this small tablet. I mean, it's about the size of a piece of paper. And so this is like taking everything I would do on the blackboard and writing it over and over and over again on a small piece of paper. And I think my hands are finally losing it. So addition and subtraction of polynomials. And the key to the addition and subtraction of polynomials ends up being our friend distribution. The distributive property. I was not lying to you when we started this semester that everything we do comes back to those first few rules that we did. And that's why I spent a lot of time talking about those rules, so that when we dug into something completely new and there were extra variables and all this weird stuff all over the place, I could always point back to those rules. And it didn't look like the rules got us much, but by being able to build everything out of them, we can make some really complex things. And that continues on. And so this rule of distribution says, hey, let's say I start over here, right? And so the thing I want to focus on is that I repeat this a part. And so I have 3x cubed plus 4x cubed. Well, that's the a part. It's the part that's repeated. So this is exactly the same if I pull my x cubed out front. Of adding the coefficients in front of them. And the number in the front we call the coefficient. And so I have 7x cubed. And so it comes from this distribution thing we've done. And I know when we did basic algebraic expressions, I think I walked over this probably in as much time as I'm doing it now. But this is worth repeating because it gets summarized as called collecting like terms. We lose what's underlying the hood, where we're applying this distributive property, because we're going to call it a new thing, collecting like terms, and we look for like things, and we add or subtract how many of them we have altogether. And I think in English that's an easier thing to say or do, but the pattern underneath it. So I can have a very large polynomial. I'm going to switch to my sky blue again and collect like terms. So I can have a very large polynomial. So, and we'll have a tendency when we learn these that they get put in parentheses, because parentheses are that bucket, right? Anything in a parenthesis we treat as one number, one quantity, right? So I'm treating this polynomial as one thing. In fact, if I'm going to use my word choice correctly, it's a trinomial because it has 3 terms. I've written it in descending order by power. And I'm going to add to it another polynomial. And so we have the ability to do an addition of these things. Now, right now, this is an abstract mathematical problem. We will, over these last 3 classes, turn this into something less abstract, okay? But I want to appreciate what we've done, right? By the parentheses, everything in the parentheses represents a quantity. I don't know what x is, but I'm carrying it around as if it's one thing. And I'm carrying this around if it's one thing. And that's possible to happen. Where this trinomial came from might mean something to me, whatever that quantity is, and I can add to another quantity. This is taking 2 rules and blending them together. All right, so one of the things is because this is addition and it doesn't matter the order we do additions in, we can get rid, or the association, the associative property, we can get rid of the parentheses. Now, plus and minus will be this. And so I've now created one larger polynomial from the two that were being added. Since polynomials are a collection of additions or subtractions of terms, when I add another one, their terms are going to come together. And now I'm going to do the game of collecting like terms. So I'm going to look for anything that has the same name. So I think I'll put a triangle. I'll use colors. Let's see. So all the x squares are yellow. So I have 8x squared minus 12x squared. Let me use green for the x's. So I only have one x, that's plus 3x. And I'll use red for the constant. So I have positive 4 and positive 7. And so I've written my like terms together. I've put all the squared terms next to the squared terms, all of the first degree terms next to the first degree terms, there's only one, and all of the constants together. If I have 8 of these, minus 12 of them, I end up with negative 4 of them. I still only have 3x of those. And 4 plus 7 is 11. And so my final polynomial, I'll revert back to my blue. And so our goal with adding or subtracting polynomials is that we write them in descending order, and each named part is only listed once. So I start with my highest power of x, then I go down to my next power of x until I get to my constant, which has no power of x in there. I'm going to do another one here. I'm going to add 3 polynomials together. And this whole process is called collecting like terms because I brought together the like things. I'm going to continue to keep blue for my answer. So or for my problem. So I have 9p squared plus 4pq plus 2q squared, that's one term, plus negative p squared minus 5q squared plus, I'm going to write the next polynomial down here, 2p squared minus 3pq minus 7q squared. All right, so I've done a little shaking up here. This is actually a common format to see in 2 variables. Again, the book says it's not going to do many of these. I said there might be 1 or 2 questions. This happens to be the format of one of them. I have written this in descending order of P and rising order of Q. I write in orders like that so that I can find like terms. So the first term I have, which let's see, Roy G. Biv, so we'll start with red, are squares, p squares. So I look for everything that has a p squared. Those are the same named terms. They're my like terms. So I start with 9p squared minus p squared plus 2p squared. Because the degree in the name of the monomial terms, I want to put all of the similar ones together. And so all the p squares come together there. All right, PQ is my next name. And there are all my PQs. So I have 4PQ minus 3PQ. Really have to make sure I get tails on Q's. And then in my last term is the Q squareds, and I'll do that in yellow. So there's Q squared, there's Q squared, and there's Q squared. I'll do it down here. So the first one is plus 2Q squared minus 5Q squared minus 7Q squared. And so bringing together the like terms, well, when you add polynomials, you're going to add all the similar terms together. So our idea of combining like terms is what addition and subtraction do. Polynomial is built by additions. If I continue to add to it, I'm rearranging the polynomial or rebuilding it. So let's see, I have 9 p squares minus 1p squares plus 2p squares, so 9 minus 1 plus 2, which is 10p squares. I think the hardest part is saying these things. So 10p squares. I have 4 PQs minus 3 PQs, so that's plus 1 PQ. Get my tails on my Q's. I have 2Q squares minus 5Q squares minus 7Q squares, so that's 2 minus 5 is negative 3, so I get negative 10 Q squares. And I'll write my final polynomial all in blue again. 10p squared plus pq minus 10q squared. And I know, a lot of you in your head are screaming, what are we doing with this? Right? These are not giving us answers. We're manipulating form. And we're looking at the rules of how this form comes together. We've got to build these polynomials until we can use them. It's a new thing for us, right? Just like when you're learning your multiplication tables, you learn the rules of multiplication coming together, then you start using it. Here we're looking at these patterns and how I can take this mess and make it into a less messier mess. I can make it so that I only see each monomial listed once, and I have how many times each listing is. That's the purpose of this, because we're going to be taking quantities in these forms and putting them together. If I want to start plugging numbers, if I were to tell you P is 1 and Q is 5, if you were to go in here and put in 1 for each P and 5 for each Q, it's a lot to type in on the calculator. But if the pattern simplifies down to this, well, you can put 1 in here, 5 in here. And so that becomes 10 plus 5 minus 10, 5. So there's a chance you can actually do it in your head versus the calculator. Here, I couldn't do that in my head, knowing what P and Q is. That's the goal here, is we simplify this thing so when we know what our P's and Q's are, it's easier for us to calculate. We get it in the simplest form, just like we reduce fractions. We're manipulating this pattern so it's an easier pattern for us to deal with. And I hope you could at least concede that if this represented something you needed to calculate, which is what it does in the end, what variables do, and this was the same thing, which is what this is telling us, this is the same thing, you would definitely run to this to put in your calculator. Right? And if you had to enter that in every 100 times a day because the calculation mattered for something you were measuring, you would do it in its simplest form. And that's the tools we're learning right now, is how to simplify something that we've gotten from a lot of parts into something that's easier for us to manipulate. Out of that, we're going to see some more patterns. Yes, combining like terms is different than the power. So Janine asked, is combining like terms different than the power rules? When you're combining like terms, that we're adding and subtracting. So just a really quick overview. The power rules said if I'm multiplying, and I'll use x, things with the same base but possibly different powers, we added the powers. And so it was based off of a multiplication coming on. Like terms say, if I'm adding things, if they have the same named part, that means the base and the power have to be exactly the same. I count up how many of them I have. Now, visually, because we borrow visually on how we line things out, it's very important to watch the symbols here to keep our rules together. One thing about this is I'm just going to change this slightly. Because these now have different powers, I have no way of combining these. For addition to work, these powers have to be exactly the same, and the name of the variables have to be exactly the same. Just like for this multiplication to work, the base had to be the same. And that's why I focus on the word monomial name, and I think of this as the name of the place. This is the x squared bit. Wow, this is the p squared bit, and this is the pq bit. On this last one, no, they would not combine. No, they would not. So Janine said the 4 and 5 wouldn't combine on this one. There's nothing I can do with this, because their names are different, right? I think of this as its name. This is the 4x cubed, and this is the 4x or the 5x squared. And cubed and squared are different things. Well, here, this is 4x squared and 5x squared. Their names are the same, so they can come together. And I wouldn't say you couldn't simplify. You're right, it wouldn't simplify any further. This is the simplified form. Slight change in the English language there, but I think it means what you're thinking. All right, let's look at cleaning the blackboard a bit. I do not like whiteboards. I do not like whiteboards. I do not like whiteboards. I tend to be really bright on the computer. I really have. If you're using computers, man, when did I start working constantly in computers? Wow. 23 years? 24 years? Even though all the music stuff I did before was computer-based and well, not computer-based, but so I've been, well, we'll say since about 1981. Yeah, about 40 years using computers. They kill my eyes. And the why I choose the black screen with the neon colors in it is modern computer is a light with little screens that open or close. So there is a light behind this, and the pixels open or close. And so a white screen is a lot of bright light in your eyes. And I found it just strains my eyes over time. So the reason I use this black screen is it's not as straining on my eyes if I'm doing a computer presentation with it. And I noticed that the guy from Khan Academy started doing that, and I borrowed that before I even thought I was going to teach. It was just easier on the eyes. So that's why I choose this pattern. One of the things I'm slowly finding is the color combinations that pop stand out to be legible. Like some of the blues, the darker blues don't, even though they're in the same color palette as the brighter color. So you see I gravitate towards the yellows, the greens, and the sky blues. I'm not a big fan of red at all, but I'm trying to color code things a lot, so my reds pop in. So a little digression there. What I'm going to do is we've done addition, and we looked at how we combined like terms. Well, addition has its friend subtraction, and to be honest, there is just one trick to subtraction. And so I'll go back to we defined. Hey, are you guys back? So we're going to look at subtraction, and we're going to do our definition of subtraction was if we had A minus B, it was the same as adding the opposite of B, right? We talked about the negative sign being an opposite. It doesn't always mean it's the negative number, it's the opposite. Well, we can do that with a polynomial. So I'm going to take a really large polynomial and I'm going to subtract another polynomial from it. Whoops. I think I'll continue to use sky blue, or as they call it in this, RGB cyan for the problem itself. So this is a fourth degree polynomial with the powers written in descending order. Fourth degree polynomial with my powers written in descending order. Now sometimes you'll get a polynomial, especially when you're first doing these in the book problems where they're not in descending order. The first thing I do is always put them in descending order. And I'm going to subtract from it another polynomial, fourth degree, in descending order. Whoa, I think I just fit that on one line. I think I might have just fit that on one line. Yes, the one just slows on the edge of the screen there. Oddly proud of that. And so we're going to take this idea, if this is my A and this is my B, I want to turn this into an addition. So I have to take the opposite of this. So I want to keep A out front. I'm going to get rid of the parentheses on the A, because I don't have to worry about A. A has nothing in front of it, so I'm not going to worry about A. But this negative sign, I'm going to distribute to every term in here. So I'm going to make the opposite of B. So what I'm going to do for that is I'm going to think of this as a -1 that's going to be applied to each thing. So this negative sign has to get applied to each term or distributed through. So negative of a positive is a negative. Negative of a negative is a positive. Oh, I'm falling on my arrows here. Let me just dip down just a little bit because I'll get rid of my arrows and I'll put them up above. Aha, I knew there was a reason. So the negative sign has to go to that term, to that term, to that term, to that term, and to the last term. So the negative goes through each part. So a negative times a positive is a negative. Right? And that is to the fourth power. X to the fourth power. A negative times a negative is a positive. So that's x cubed. Negative times a positive is a negative. That's my x squared terms. And negative times a positive is a negative. And a negative times a positive is a negative. And so I have switched this from being subtraction by distributing that negative to everything in there. And that is what our definition of subtraction did. Now for large polynomials, there's a lot of terms that need switched. But in general, we just change the signs. Right? There's different ways of thinking of what subtraction is. Right? When we said the opposite, we took the opposite sign of whatever b had. And so we take the opposite sign of what every term in here has. That's one way of thinking about it. I think about it as, if you notice when I was using my word choice here, as a multiplication. I'm thinking of this as a -1 out front, and I distributed -1 to every term. They're mathematically the same end result. They don't change, and you just have to have a process you hold in your mind for it. So now I'm going to start with yellow, and I'm going to grab all my fourth power terms. So I have 3x to the fourth minus 2x to the fourth. There's my fourth power terms. I'm going to go to my third power terms. So I have a positive x cubed plus 5x cubed. I'm going to go to my x squared terms. So I have minus 4x squared minus 4x squared. Let's repeat it there. And now I'm going to go to my x terms. So I have 8x minus x. And then my constants. I'm running out of colors. I'll do orange. So -9 minus 1. -9 minus 1. And so I've gotten all of my like terms together and almost made a rainbow. Right? Polynomials get big. So let's focus on the first term. 3x to the fourth minus 2x to the fourth is one of them. 1x cubed and 5x cubed is 6 of them. Minus 4x squared and minus 4x squared is -8 of them. 8x minus 1x is 7 of them. And then -9 minus 1 is -10. And so I collected my like terms after propagating this negative through the polynomial that's being subtracted. And so I finalize and write my final polynomial, which is much more simpler than the two polynomial forms. All right, so the worksheets on Blackboard for chapter, I want to say it's 15 in here. Let me look. I'm walking over to Blackboard now. Is it my iConnect logs off and I have to log back in? Did that in the classroom all the time too. If I had iConnect up, I would have to log back in a lot, which is why I don't like the computers in the classroom. Well, one of the reasons I don't like I'm just a grumpy for loads of things. Let's see here. Where is that? So in-class practice worksheets, which are in the course content in Blackboard, I want to say chapter 15 is the one we should be working on. So what I'm going to do right now, I'm going to download that. And I am sending this out to you directly if I haven't already. chapter 11 in the book worksheet. I'm sending you guys out the worksheet that I'd normally be doing in class. You should be doing everything up to section 4 in this worksheet. This is stuff we need to be practicing. These are really, really odd concepts because they're new to us. Or if they're not new to us, we really want to put them in perspective. And I find the best way to do that is practice. So I would work on this worksheet I just sent you up to section 4. That's everything we've covered in this chapter on polynomials. And we can go from there on working on this. Just to get a feel of how we manipulate these things. Right? And fire me off questions. I have some videos I'm going to record. If there's any examples, problems you want an example of, point it out to me. It takes me about 24 hours to record. Heather and Ryan are waiting on 2 things from Pearson, and Tina had 1 thing in Pearson that she got right but Pearson had wrong. I'm noticing that happens in the way they randomize questions. Sometimes their randomization breaks. Hasn't been often, but now that I've constantly on Pearson, I'm picking up more of them than I did before. So that's everything I have here. We've just did addition and subtraction, so guess what the next thing? We're going to do multiplication. And multiplication is the if you continue on into the functions class or 126, multiplication and factoring of polynomials is the really important part for solving things. The trick you will see, and I will make sure I emphasize it, is we turn things linear when they're not. And so these higher order polynomials, if we can break them apart into factors, we can turn into lines. Well, math is dual directional. If I can break something apart, I can also put it back together, right? And I hope I emphasize that a lot for you here, is that we're putting things together, going back and forth. Everything we do, we have a reverse process for it. Because that's the really important part. You don't know which end you're coming into on a problem, and so you want to be able to go in both directions for all the math that you have. And yes, curse you, Pearson! But at least it gives us something to share, right? Hey, all right. It was a pleasure being with you. Sorry for the little hiccups in there. They're just part of the tech. Everyone have a wonderful day. If you need anything, please email me. Be safe. Be well. I really, really hope to see you again in person soon.